Let's continue our conversation about modern physics. In our last episode, we learned that there were several phenomena found in nature that seemed to contradict the idea that light is a wave and required a different picture of light. And we learned a little about the photoelectric effect and the Compton effect. And finally, we learned about line spectra and hydrogen, where light from hydrogen was sent through a prism. And when the light went through the prism, they found out you didn't get a rainbow, but you only got 4 specific colored lines, and nobody could explain that. And we had said that a new theory was needed. So now we're going to talk about that new theory. Now the name of that new theory is called the quantum theory. So we're just going to start out by talking about some of the basic terminology and ideas of it, and then we will try to illustrate and show applications of it. So first of all, quantum theory says electromagnetic energy is emitted from and absorbed by matter only in discrete amounts or packets or packages, and a package is called a quantum. The amount of energy of a quantum is given by a formula, E equals h times f, where h is a new number called Planck's constant, which we have on the front page of our reference tables, and f is the frequency of the radiation. A quantum of electromagnetic energy is called a photon. This is just terminology. A photon is what we call a package of electromagnetic energy. So we would say that energy is quantized. Now this idea of something being quantized, we've already seen that before. We have said that electric charge is quantized. So there is a number called the elementary charge, and that things that are charged can only have 1 elementary charge, or 2 elementary charges, or 3 elementary charges, but you can't have 2.7 elementary charges. So what we can say is that photons can have 1 h times f of energy, or 2 h times f's of energy, or 3 h times f. So energy comes also in packages. It is quantized. So let's see what this looks like on our reference tables, and then we're going to try a practice problem. This is our key formula right here. The energy of a photon is equal to h times f, and on our reference tables they also write that as hc over wavelength. So let's talk about a couple things there. First of all, h, Planck's constant, is an incredibly tiny number, 6.63 times 10 to the negative 34 joule seconds. So that means that with any frequency of light, because this number is so tiny, the energy of a photon is very, very small. Now notice also that in this formula they kind of write it 2 ways, and that's because we can also use our familiar formula from waves, which is the speed of a wave is frequency times wavelength. But when we're talking about light, the speed, v, of the wave is just the speed of light. So we actually can write the wave formula this way. Speed equals frequency times wavelength. So what they've done up here is they've solved for f. So let's do that. If you solve this for f, you get f equals c over wavelength. Divide both sides of this by wavelength, you get f is c over wavelength. So instead of h times f, you can write h times c over wavelength. So let's see how this all works in a problem. So we're going to try this problem. What is the wavelength and energy of a photon of violet light? So first of all, what I need is some information about violet light. So what I'm going to do is go to my reference tables and find the table that has the electromagnetic spectrum, and it's got the colors listed. Okay, so here's my electromagnetic spectrum, and here is visible light, this little slice right here, and here's violet right here. So I can see these are the frequencies that are listed here for each of the colors. So I can see the frequency of violet light is 7.69 times 10 to the 14th hertz. So let's write that down. Frequency of violet light is 7.69 times 10 to the 14th hertz, or per seconds. Now, wavelength is related to frequency through this formula. Speed of light equals frequency times wavelength. So if I want the wavelength, I'm going to solve for it here. Wavelength is speed of light over frequency. And the speed of light in a vacuum is 3.0 times 10 to the 8th meters per second. And I divide it by 7.69 times 10 to the 14th hertz, or per seconds. And I get a wavelength of 3.90 times 10 to the negative 7 meters. Now, to find out the energy of a photon of violet light, I'm going to use the formula that I just learned for calculating the energy of photons. And that formula is E equals H times F, where H is called Planck's constant. So E will equal Planck's constant, which I look up on the reference tables right on the front page, 6.63 times 10 to the negative 34 joule seconds. And I'm going to multiply that times the frequency that I just looked up, 7.69 times 10 to the 14th hertz, which are also per seconds. So both of these numbers I just looked up on the reference tables. So the energy is 5.10 times 10 to the negative 19 joules. Now, before we leave this problem, let me also show you something that can be quite useful to us later on. We just figured out that the energy of a photon of violet light is 5.1 times 10 to the negative 19 joules. Now, sometimes it will be important not to use joules, but to convert to a unit called electron volts. You may have remembered this from back when we did electricity. On our reference tables, there is a conversion factor that 1.6 times 10 to the negative 19 joules of energy is called 1 electron volt. So we can also get the energy of a photon of violet light in electron volts. So let's do that. So what I'm going to do is take energy of this photon in joules, 5.19 times 10 to the negative 19, and I am going to divide it by my conversion factor of 1.6 times 10 to the negative 19 joules per electron volt, which I looked up on the reference tables, and find out that the energy of a photon in electron volts is 3.19. And this is a conversion that I'm going to need to do in the future.